and we are going to think about quantum theory of hydrogen atom. And of course, what I mean, quantum theory of hydrogen atom is something beyond Bohr model. And for us to be able to do that, we have to consider Schrodinger equation in more than one dimension, right? So far, we were only considering one-dimensional case because it was physically easier to argue about 1D, and the equations were easier to solve in 1D. But now we know what we are supposed to do, and now we have a better sense of Schrodinger equation. We can think about like more than one dimension. And I think the easiest thing to do is just to start with, again, particle in a box, but in 3D, particle in a 3D box. Okay. So basically, the potential is now a function of x, y, and z, x, y, and z, and it is equal to 0 if x and y and z are inside a box from 0 to L and infinity otherwise. Okay, so this is like if you want, this is this one is x, this one is y, and this one is z, and the length of box is L and L and L everywhere. Okay, an L cube, and we want to solve Schrodinger equation inside, but the Schrodinger equation in this case is like 3D. Schrodinger equation is minus h bar squared over 2m. Now, rather than del x, now we are going to use this inverted triangle, which is so-called Nabla operator, and it is acting on psi, which is a function of x, y, and z, plus, maybe I can put it here. I think let me use u. I think I used u in the past, so let me try it. I won't be successful. Let me at least try to be consistent. U, x, y, and z of psi x, y, and z is equal to E times psi x, comma, y, comma, z. And what is Nabla squared in 3D? So first we have to make a decision, right? What kind of coordinate system can we use for this problem? Right? Because in 1D there's only one coordinate system. In more than 1D we have options, right? We have like cylindrical coordinates, we have spherical coordinates, we have hyperbolic coordinates. As a matter of fact, there are infinitely many ways to describe a coordinate system, right? But what is the most reasonable choice for this problem? Anybody want to? Any suggestions? Cartesian? Yes. So we are supposed to use Cartesian. And the nice thing about Cartesian is it's very easy to write this Nabla operator in Cartesian. And it is basically Nabla square is equal to del x squared plus del y squared plus del z squared. And as we did in the past, like a reasonable starting point is to assume separable form and see if it works. Of course, from the symmetry of the problem, I know separable solutions are going to work, but if it wouldn't, I would see it from the Schrodinger equation. So let's try separable form. So what this means is I'm going to write psi of x, comma, y, comma, z. Yeah, I factored it like a function of x, which I called f, a function of y, which I called g, and a function of z, which I'll call h. Okay?
Is it an assumption?
Is it?
An assumption.
An assumption, yes. Right now it is an assumption. So I think safest way is just to look at the symmetry of the problem. Symmetry of problem, you can see x component, y component, and z component seem to be separated, right? Because of these like planes, you know, planes separate Cartesian coordinates. But even if you have doubts, you can substitute the equation and then see if your assumption works out. Okay, so let's do this. And I think so outside, again, I think there's nothing to write, right? Outside, v is infinity, and psi is going to be 0 outside. So I can put this in a boundary condition and forget about u, because inside u is 0 and there's nothing to separate anyways. So let me write it like minus h bar squared over 2m del squared del x squared acting on this. Actually, let me not write everything one by one. Let me keep the operator form and see how it separates. So this is y, this is z squared, and this entire thing is hitting on. Let me also skip the arguments to save some space because it's going to be long and unnecessary. F, G, and H should be equal to E times F, G, and H. When I look at this equation, I have to remember F only depends on X, G only depends on Y, H only depends on Z. Then if I hit with these derivatives, let's think about, for example, this one. So let's take this 2m. So this is acting on F, G, and H. But I know G and H, they don't know about X, right? There's nothing to take derivative with respect to X. So I can take this out. And I can just write this at minus. Similarly, I can hit this FGY with this one, and it's going to be F is Y independent, H is Y independent. So what's going to remain is H squared over 2m partial squared partial Y squared, only acting on G. And similarly for the last one, let me copy, not to. So this is going to be F and G, this is going to be Z, and this is going to be H, is equal to, okay, I need to push just a little bit, E times F, G, and H. Now I want to divide this entire equation with product of F, G, and H. So let's copy and do that. So I'll divide by 1 over F, G, and H. So if I do that, on this term, G and H will cancel. There will be just 1 over F. Here, F and H will cancel. There will be only 1 over G left. Here, F and G will cancel, and there will be only 1 over H left. And there's no FHG here. Now, it was earlier an assumption, and now it seems like the assumption is working. And let's see how. So first of all, this is an energy, right? Energy is like an eigenvalue. It cannot have like a coordinate dependence. It's just, it can be quantized, but it cannot be X, Y, or Z dependent. So I look at this equation. F is a function of X. That's what we said here. And this is like a X derivative. And technically, this has to be like d dx squared, right? There's nothing partial anymore. So it's just full derivative. So it's a constant. So this is a constant for y and z components. So I can better call this a constant name, and I want to call this E of x. Okay. And the same thing for here. So this is full derivative with respect to y, and I'll call this constant E of y. And another here, I'm going to call this constant E of z. So in total energy is going to be Ex plus Ey plus Ez. I mean constants in the sense that, so this is a constant because there's only x here, right? There's no y and z. So this is a constant for y and z components, and I call it ex. But I know, like, from the symmetry, right, x and y and z are labels I put. If I just scramble x and y and z, if I'm like in a universe where x, y, and z are different symbols, I would not know which one is x, which one is y, and which one is z, right? So if this is a constant for y and z, that's the constant for the entire equation. Because I know their sum is supposed to be constant. I know each term is independent of each other term. So I think it is not too much to ask this to be the constant itself, and so on, right? And the total energy is going to be like x plus y plus z. Now I want to focus on each equation separately. Let's take this one. So this one we called Ex. Now I can take f here and erase here. But when I look at this equation, okay, let me just make this. This is just 1D Schrodinger equation, right? So this is exactly 1D Schrodinger equation, which we solved many times so far. Is that right? And the boundary conditions are also the same, right? I'm looking at x component. So if I am just walking around along the x, if I'm inside the box, it is 0. If I'm on the wall, infinite potential, so I have to vanish here and on the other wall. So boundary conditions are also the same. So f of 0 is equal to f of, did I call it A or L? Okay, let's call it L. So L is equal to 0. Same boundary conditions, same Schrodinger equation, same solution. That's this nice thing, right? If you solve one equation for once and it comes back to you again, you can just use exactly the same thing. You don't have to redo it. Then f is going to be 2 over L sine n pi over L times x, and Ex is going to be n squared, okay, let me write h bar squared pi squared over 2m L squared n squared. Yes? This is h bar, yes. So thank you, this is h bar. So this one is, yeah, I think this one should be h bar. I think I couldn't copy it, right? So if I can do this for f, I can do it for g, right? Nothing changed. What changes is this x should be y. But like this n was a quantum number and nobody tells me, I mean, there's no principle for us to like impose exactly the same quantum number this in this equation and in this equation, right? Because these are like separate equations. So to separate that, let's also put like reminders. So this is n of x. So this is an integer. I mean, I put subscript x, but it's kind of like a bad notation. That doesn't mean it depends on x. It is independent of x, but it is the quantum number of the x component. If that confuses you, you can use like n, l, and m, for example. But I prefer to write it like that to save letters for other things. So then I'm going to call this ny. This is also integer, right? And this is y. So this is an x. So this is ny. And same thing for h. So h is this. So this is going to be nz. So this is z. So this is nz. I think this one is ey. This one is ez. Good. And each n and x is equal to 1 to ... and y is equal to 1 to ... and nz is equal to 1 to ... Now I can glue all these little pieces together to get the full wave function. The full wave function was psi of x, comma y, comma z. Now there are 3 of these, 2 over L, 3 half, and this is sine nx pi over L x. Let me copy. This one and this one. So this is nx, this is ny, so this is nz. And so this is the eigenfunction, and Schrodinger equation, as we talked, is equation, an eigenvalue equation. We need eigenfunctions and eigenvalues, and the eigenvalues are going to be e and x and y and z is equal to h bar squared over 2m L squared. Let me also put pi squared here, and x squared plus ny squared plus and z squared. And problem solved. Yes?
Inside side, that would be y.
Oh, okay. I think this one is y. This one, right? Yeah, thank you. So this is z, x, y, z. I think now, and x, and y, and z. Yes, thank you. So let's look at these solutions a little bit more carefully. So the lowest available state is what we call ground states. So the ground state. And this is like a quadratic function, and the smallest possible value is when all these integers are smallest, right? And the smallest is like in each case 1. So ground state is going to be e 1, 1, 1 is equal to h bar squared pi squared over 2m L squared 1 plus 1 plus 1, and this is going to be equal to 3 of these. Good. Simple stuff. Yes.
Why is some energized models instead of multiplying?
Because here this came from the equation, right? When we take the equation to be separable, so they were like sum of ex and ey and ez was this full e, right? Yeah. Good. Any other questions or comments? Now let's consider the excited states. Like let's consider first excited state. Now I have options, right? The first, it seems like there's only one ground state. For any other nx, ny, and nz combination, it's going to be a higher energy, right? Now I have to choose other n's, and this next available n is 2. But I can put 2 to x component, I can put 2 to y component or z component. So this is going to be e. For example, let's put it in x component, 2, 1, 1 is equal to, so this is going to be exactly the same, but first n is 2 and square is 4. If you want, these are all squares. And this is 2 squared, this is 1 squared, and this is 1 squared. So the total energy in this case, 4 plus 1 plus 1 is 6, if I'm not wrong. But this is not the only option, right? I could also put this 2 to not for nx, but I could put it for ny. Let me show you. Like I could choose 1 to 1. This would be 1, this 2, 1. But 2 plus 1 plus 1, 4 plus 1 plus 1 is equal to 1 plus 4 plus, right? Last time I checked, they are the same. So it's 6. And same for z. So this is 1, 1, 2. This is 1. This is 2. And this is again 6. So what we have here is something we didn't have in the 1D case. In the 1D case, all the energies we found were non-degenerate. Right? Now we are introducing a new terminology. So E211 is equal to E121 is equal to E112. I mean, this is not a bad thing, but the word is bad. It's degenerate. I mean, degenerate people are bad, but degenerate energy states, there's nothing wrong with that. We just call it, this is just a name, degenerate. It means they are like multiple of the same value, degenerate eigenvalues. And since there are 3 of them, if you consider, there is no best way to do this. Like, you have to consider all possibilities and make sure they are all you can list. For example, this one is 3-fold degenerate. So there can be many more degeneracies. In higher and higher states, there can be more states. And this degeneracy in this problem is actually related to symmetry, right? So if you choose, for example, 2, 1, 1, right? Yes. Yes.
Is 1 and choose refer to the axis, right?
Yes. Yes.
So how is like an electron in the x-axis in the second state and y and z is in the first?
No, it is exactly the same electron. There is like one electron, but this electron has to have x, y, and z directions, right, in 3D.
Okay.
And these 3 directions are orthogonal. They are independent of each other. They are separable. So electron, the same electron, needs to choose 1 for x, 1 for y, and 1 for z. It's the same electron. So exactly like in 3D, right? Electron can choose to go in x with some speed in x direction, another speed in y direction, another speed in z direction. Exactly like that, it can also choose 3 different quantum numbers because it's in 3-dimensional space. Okay. So suppose you have chosen, so this 3-fold degeneracy is related to symmetry. Suppose you have chosen this, right? And it is going to be, let me not write the entire, okay, maybe I can write it. So let me write the wave function like this. It is like psi 2, 1, 1, and my box is like this, right? You are supposed to be inside the box, and this one is x direction, this one is y direction, and this one is z direction. And in the x direction, by the way, these are very nice to plot with something like Mathematica, but I didn't prepare it for this time. In the x direction, you have this, right? Because n is equal to 2, so this is x direction. In the y direction, you have just this is y direction, no node, because n is equal to 1. And in the z direction, you have this, no node. But suppose you prepared this system and you went to buy a coffee or something, and your friend came and rotated this box, right? Rather than, okay, this face looking here, your friend rotated it like this. There's no way you would know this. Nobody would be, not only you would not be able to tell it, there is no experiment in the world that can tell the difference. If the box is rotated, that's it. So this box, this face looking at us, and the box looking on this side are exactly the same from the physics point of view. Then the energies should also be the same, because energy is observable, but the wave function is not. We should have the same energy for these 2 things to be indistinguishable. Then you can see the symmetry that we enforce is causing a degeneracy. And that's actually a general principle in physics. Whenever you have symmetries, there are degeneracies corresponding to symmetries. Yes?
So we can express a wave function as an energy or momentum eigenfunctions.
Right now, yes.
We have the general eigenfunctions, so should we express them as momentum eigenfunctions, then express a wave function in terms of momentum eigenfunctions?
But like, so this, you can consider about this problem in 1D, it's exactly the same problem, right? In 1D, we considered this, right? We said, let's first solve these exact eigenstates, and we find these signs, and we said, let's see if there are also eigenfunctions of momentum. Like we hit with this p momentum on this 2 over L sine n pi over Lx, and we found that it was not equal to something. For something to be eigenfunction, okay. For something to be eigenfunction, what do we require? We require here a number and the same thing. Okay, my pen is behaving. But in 1D, we showed that this is not satisfied. So exactly the same thing happens here. They are not momentum eigenfunctions. Because for each component, x, the wave going to the right is degenerate wave going to the left, and to satisfy the boundary condition, you take them together, which breaks this momentum translation.
The generality you said here, I expressed that as a momentum eigenfunction, right?
Well, it depends on the problem. I cannot say it like that, but this degeneracy is like rotational symmetry. Momentum is about translation. Translation and rotation are completely different things. I don't think there's like a general principle. When there's like a degeneracy, it would be momentum. I don't think there's such a thing.
John,
Mm-hmm.
if the states of electrons are like separated over this tree, when x is 1, y is 1, and z is 2, as an example,
Mm-hmm.
what is the state of electron? Like, is it in the ground or second?
So why is that a state of electron?
No, what is
What?
the state of
What is the state of electron? The state of electron is this, right? 1, 1, and 2. What is the eigenfunction? Here. Put 1 here, and 2 here. That's your state. That's the quantum state. By the way, this depends on nx, ny, and nz, but I didn't write it. And that's it.
So an electron can be the third state in y-axis and first
Mhm.
state in x.
Exactly.
How
All,
is the motion then? Like,
So there is nothing like conflicting in that, right? Like you have this full wave function, and in this wave function, nx, ny, and z are completely different, right? You have to choose 3 numbers in 3 dimensions.
in our model, as you showed us, like
Yeah.
we've seen so far like
Mm.
circles,
Mm-hmm.
and all those circles were kind of symmetrical. Each state.
Yeah, we are going to
gets
come to that.
bigger.
Like now in 3 dimensions, right? We have like different circles to choose. Why am I supposed to choose like right? I can choose like maybe like a circle, a little bit on top, maybe a little bit on the bottom. Maybe I can choose like an ellipsoid. All these things are possible. But for that, for us to be able to do that, we have to think about Schrodinger equation in 3D with this 1 over r potential, which we'll come to in a little bit. But now this is not like Bohr model, right? We break rotation symmetry by choosing this box, so it is different by symmetry.
John, what was the relationship with n and number of nodes?
N and number of nodes. The first one has no nodes, the second one has 2, right? 1 node. If you look at the third one, it's going to have 2 nodes. Every time you increase the quantum number, you increase the node.
John, n can take any integer, right?
Yes, n can take any integer, any positive integer, 1, 2, 3 to infinity. So in the energy level diagram, like we show these things like this. For example, in 1D, we were showing it like E1, right? There was like something like E2, and there was like E3, and these were all non-degenerate. So sometimes we'll have to draw energy level diagrams, and what we are going to do is like we are going to draw one line. So one line, one more line, and one more line. Of course, if I were to draw all of them on top of each other, I wouldn't know there are 3 lines. but for drawing purposes, we just shift a little bit. And sometimes we are going to do something to the system, like to break this rotational symmetry. That's what we call perturbations. Like we are going to like solve the problem, and then we are going to consider a little bit of deformation. Whenever there is like a little bit deformation, we are going to say this degeneracy is split, and then we are going to have like this opening, right? So if you want, this is like E211 is equal to E121 is equal to E112, but these are not like that. Maybe it's like E211, maybe this is E121, maybe this is E11 and 2. And they'll be like splitting. We are going to say they're like maybe a gap in between these states. So right now we don't have that, but I am trying to familiarize you with the jargon from this simple example. For example, a good way to split the degeneracy, here's exercise for you or optional homework. Show that if you take Lx not equal to Ly not equal to Lz, so basically the dimensions of the box are different. It's not a perfect cube anymore. Then let me write it. Degeneracy is split. Okay. Simple thing to show. You just write it and look at it and conclude that they are different things. Any questions or comments? If not, I want to consider, so this was like a toy model for us to be familiar with what's going to happen in more than one dimension. So now let's consider something more realistic. Let's consider Schrodinger equation for hydrogen atom, which is going to be Bohr model, like you asked. But there will be like much better and much better resolution. So let's first choose the coordinate system. Of course, the potential, I think I used U or V? I think I used U, right? Okay. The potential is U of R is equal to minus 1 over 4 pi epsilon naught E squared over R, right? So basically we are saying that proton is much bigger than electron. If you want, we can go from like this proton and electron coordinate to center of mass coordinates, and because proton mass is much bigger, maybe like 2,000 times bigger than electron, the center of mass will be almost on top of proton. And we can say that, okay, then what matters is the distance between electron and proton. We can assume the proton to be fixed in the center of the coordinate system. So then proton is at the center, and there's like a central potential located at the location of the proton, and that potential is given by Coulomb's potential, right? This is Coulomb potential. So that's what we need to solve. And because of this potential, right, there's like a radial symmetry, because as soon as I write R, I know this is going to be like a radial coordinate problem, because there's R. If I were to write X and Y and Z, R would be what? R would be X squared plus Y squared plus Z squared. And not only that, there's also 1 over. That would be like a terrible thing to do, right? So it's more reasonable to use, based on the symmetry of the potential, exactly like a box. I already anticipate the necessity of like radial coordinates. Then let's think about the radial coordinates. So these are like so-called Cartesian components, X, Y, and Z. and there's like r, which is the length of this red vector. So here is so-called azimuthal angle theta, and this one is this is polar angle theta. This one is azimuthal angle phi. Any engineers here? Anybody from engineering? So you use the other way, right? Phi for polar, theta for. So sorry about that. There will be confusion, but that's also your book. Sorry about that. And the first thing is the coordinate system. The second thing is, because Schrodinger equation has this h bar squared over 2m del squared psi plus u of r psi is equal to e psi, I need to also determine the nabla in spherical coordinates. And again, don't be scared. You can just look at the Wikipedia. I'm just going to write it for you. Nabla in spherical coordinates is, okay, let me write nabla squared acting on psi is something like that. So this is 1 over r squared del r squared del psi del r plus 1 over r squared sine theta del theta sine theta del psi del theta. I think I'm going to run out of space. Maybe I can shift the entire thing a little bit. And plus 1 over r squared sine squared theta del squared psi del phi squared. So if you don't remember it, that's fine. I mean, if I'm working with this for a couple of days, I remember to write it, but a couple of weeks later, I forget. So I have to every time go look at it and write it. So I don't expect you to write this from your heart, but if you can do, that's great. Congratulations. So this is the first thing. Maybe I just advertise you what's going to happen and then finish it there. What we are going to do is, so this is the nabla in spherical coordinates. So this is spherical coordinate Laplacian. And we are going to assume, again, separable form. So assume separable form. So psi is going to be r, theta, and phi is going to be a function of r. We are going to use r for r component. We are going to use uppercase theta, which is kind of ugly, but that's the standard, so I'll also use it. Theta of theta and uppercase phi of phi. We are going to substitute it here. I mean, not there, this is just Laplacian. We are going to substitute it here. And we are going to hope that we can do exactly what we did for the box. And we are going to separate the equations. We are going to have like an R equation. We are going to have like a theta equation. And we are going to have a phi equation. Not only equations, but also one more thing, right? What is the most important thing to label these things? There will also be 3 quantum numbers, exactly like nx, ny, and nz. But the difference in the spherical coordinates, they are not going to be independent of each other. Because of this 1 over r, 3 quantum numbers. and we are going to use N, L, and M, but they will not be independent. There will be like some very nice relation between them, and that will be the key for us to understand hydrogen atom and like many things about hydrogen atom.